Okay, so I think we can start. We have a pretty good attendance, so thank you for coming to this webinar today. Hello and welcome to this first course of ReSonate, which will be dedicated to the production of a radioactive ion beam with the ISOL method. A second part of this course on the in-flight method. This time will be presented by Hugo Guérin on the 2nd of February. So in 3 weeks, same day, same hour, but it will be advertised via the ReSonate mailing list. Today, the session will be presented by Vincent Bosquet, who is currently a postdoc at LPC Caen and that did his PhD in the ISOL team in Gagnon. So Vincent, the floor is yours.
Well, thank you very much. So first, I would like to thank the organizer who have kindly invited me to give this talk. And so does it work? Yay. So the title of my presentation is How It's Made, Radioactive Ion Beam, the ISOL Way. Everybody here is familiar with the nuclear landscape. So in nature, we have access to 251 stable nuclei, but there is over 3,000 radioactive nuclei. So what to do with radioactive nuclei? Well, we can do a lot of stuff. We can study decay, do precise mass measurement, have access to more nuclear reactions, do standard model tests, do medicine, astrophysics, material science, etc. But the question is, how can you make radioactive nuclei? So a very crude way would be to use a nuclear reactor. So that would produce a lot of isotopes. But then you will need to do chemistry to separate them. And then you'll be able to observe your radioactive nuclei. This method is very slow. It's chemistry dependent. And it does not access exotic nuclei because it's very slow. Another way would be to send a beam directly into a target and then put a detector around it and measure the product of the nuclear reaction. This method has the advantages of being very fast, but it's non-selective and it's very noisy because all the nuclear reactions are happening at once at the same time. So wouldn't it be nice if we could have radioactive nucleus sent far away from the production target, which is very polluted in terms of nuclear reaction and radiation, have very little contaminant, have a high number of nucleus of interest for statistics purposes. It would be also nice to be able to manipulate the nucleus. For instance, we could accelerate them, transport them, slow them, trap them, or implant them. And it would be also very nice to be able to make secondary nuclear reaction with them. And the answer to all of this problem is using radioactive ion beam. There is two main methods to create a radioactive ion beam. And the first one would be to use the in-flight separation method. And so to do so, what you would do is to use a primary beam made of ions, send these ions onto a thin target. The radioactive nuclei produced in the target will then leave this target, be separated using a magnetic and electric device. And then you would end up with a radioactive ion beam of the nucleus of interest. The advantages of this method is that it allows access to short-lived ions that have an half-life higher than a few microseconds. And also the beam would already have a few mega electron volt of energy. The disadvantages of this method is the target is relatively thin to allow radioactive nuclei to leave the target. And so the production is not that big. And also the characteristic of the beam that is produced are fairly poor. For instance, they have a very high beam emissivity as well as a high energy dispersion. And to have more information of this method, I invite you to follow the talk given by Hugo Guérin that will happen on the 2nd of February. And the second method, which will be the topic of this talk, is the ISOL method. ISOL stands for isotopic separation online. In this method, you would use a primary beam that could be made of ions, electrons, neutrons, or gammas. You would send them onto a fixed target where a lot of nuclear reaction will happen. The radioactive nuclei will then be extracted from the target, transported through a transfer tube inside an ion source. The radioactive atoms will then be ionized and they will be separated using, for instance, a magnetic dipole, and you will end up with radioactive ion beam. The advantages of this method is that the properties of the beam created by the ion source are very good. For instance, they have a small energy dispersion and a small angular dispersion, and that allow to easily manipulate the beam. So the beam can be post-accelerated, and thanks to this very fixed target, you usually have a high production rate. The disadvantages of this method is that it's quite slow. The transformation time from the production up to the extraction as a radioactive ion beam can take from a few milliseconds to days. And so it is very chemistry dependent. And so for the layout of my talk, first I will show you a few of the first ISOL systems ever made. Then I will show a short, sorry, a very, very quick presentation of the ISOL facility around the world. And I will go in depth into the physics of all the steps involved in the ISOL method. And then I will give you a short tutorial on how to check if a beam is doable. So the very first step, 1951 in Copenhagen. In the paper written in 1951, there is this specific sentence. The cyclotron and the isotope separator were operated simultaneously. That means that the production inside the target was performed at the same time as the ionization. In this specific setup, they had a target made of uranium that was impinged with a neutron beam to produce fission product. Only the gaseous product of the fission, so in this case krypton, were extracted from the target and transported through a 10-meter long tube inside an ion source. The ion source is located on this figure, it's the one number. Then the ion beam is focused using electric lenses, and then this radioactive ion beam is separated using a magnetic dipole, and then the purified ion beam is sent onto a decay station. And this specific installation has been able to produce radioactive isotope of krypton with half-life going up to 10 seconds, which is relatively fast for the time at least. But this setup in itself is quite slow, mainly due to the fact that they are using a 10-meter transfer tube between the target and the ion source. The second step happened in Louvain-la-Neuve in Belgium in 1989. In this facility, they were using a beam made of proton or helium-3 at an energy of 30 mega electron volt. The target material that have been used is either carbon, lithium fluoride, boron nitrate, water, or just plain table salt. The ion source that has been coupled to the target are of the electron cyclotron resonance ion tube, and you can see a few of the beams that have been produced for helium-6, carbon-11, etc. Using other cyclotrons, they have been able to post-accelerate the radioactive ion beam to perform experiments with them. And now I will show you the main player that started in 1967. Sorry, 1967 up to these days. So the ISOL facility is the main and historical facility in the world. They have a proton beam that has an energy of 1.4 giga electron volt, so very high energy. And they've tried probably almost all of the target material imaginable. So a lot of carbide, uranium, thorium, silicium, and titanium carbide, and also some other targets like calcium oxide. They have been using all the ion sources, surface ionization, resonant laser ionization, electron impact ionization, you name it. And on this periodic table, you can see all of the elements that have been produced to this day in ISOL day. So this facility has been quite proficient, and they have been producing almost all of the elements. Okay, and now for the RIP facility in the world. So this graph shows all the ISOL type facility in red and all the in-flight type facilities in black. So you can see there is quite a lot of them on this plan. And we can't explain all of them. So I'm sorry, I won't go in depth on all of these facilities. Okay, so the ISOL method, it's a multi-step process. And let's delve into the physics. So what are those steps anyway? So I've already shown you this graph. So it has several steps. The first one is production. You have a primary beam that creates radioactive isotopes inside of the target. Then the second step is to extract these radioactive isotopes from the target. And this process is called diffusion. And then you would transport these radioactive atoms from the target to the ion source through a transfer tube. And this is called effusion. Then the next step is to ionize these radioactive atoms. And then once they are transferred into a radioactive ion beam, to separate them. So how to predict radioactive ion beam yield? There's a relatively simple formula. The radioactive ion beam intensity would be equal to the production inside the target times the release efficiency times the ionization efficiency. The production part, it involves nuclear reaction. The release part involves release from target and transport to ion source. And the ionization involves ion source stuff. And so guess what happens if one of these terms is zero? Well, we all have PhDs here. You get zero radioactive ions. So 0 times something equals 0. Yeah, math. Okay, let's continue. Now for the production. One of the methods that is mostly used in the ISOL facility is induced fission. In induced fission, you would use a very heavy isotopes. You would send a light projectile on it to induced fission, and you will end up with fission product. The fission product usually have mass and a charge that is half of the target. You would have a typical target that would be made of uranium carbide or thorium carbide, and the typical primary beam would be proton, neutron, or electron in some cases. This is the classic ISOL reaction. It has the advantages of producing neutron-rich isotopes and to produce quite a lot of them. And on this graph, you can see the nuclear production cross-section for a beam at 1 GeV of protons sent onto a uranium-238 target. Another production method, which is mostly used in Spiral 1 at Ganil in France, is fragmentation. In this reaction, you would send a medium mass nuclei onto a medium mass target at an energy of 50 or 90 MeV per nucleon, sometime higher. And what will happen is that you will have a collision between the two nuclei that will create target fragment and projectile fragment in a highly excited and highly deformed state. This projectile and target will then de-excite and produce a lot of radioactive isotopes. And on this graph, you can see the beam that have been produced or will be produced at Ganil, mostly via beam fragmentation. And you can notice that the production is centered around the valley of stability. Another production method is fusion evaporation. Fusion evaporation works as follows. A projectile is sent onto a target slightly above the Coulomb barrier. It ends up into a compound nucleus in a highly excited state. It will then decay by emitting a few nucleons, and you will end up with a radioactive nuclei. This method of production is suited for the production of neutron-deficient isotopes, but it requires relatively heavy ion beam, so not all facilities are able to provide this. This method of production is somewhat selective. And on the graph on the right, you can see the area of the nuclear chart that would be populated if we were to use a beam of chrom-50 at 5 MeV per nucleon onto a target of nickel 58. And the takeaway for production are as follows. Different reactions populate different area of the nuclear chart. For instance, fission provides neutron-rich nuclei. and fusion evaporation provide neutron-deficient nuclei. The available reaction is facility dependent. That's quite important. You won't be able to produce every isotopes in every facility. And the beam target combination matters. This is what will mostly drive what kind of isotopes you will be able to produce. And there is other production reaction like spallation, transfer reaction, and photofission. Okay, and now for the second process of the ISOL method, the release from target. So for this example, I've taken a target made of uranium carbide with a proton beam. The proton beam induces fission inside of the target. The fission product will be emitted from the uranium, and this fission product will be thermalized and neutralized inside of the target material. And the question is, how do we get radioactive atoms out of the target? And the answer is a lot of heat. And so we are not using open flames. This is not how we do things. Most of the time, we are using a heating that is provided by electric resistive heating and the energy deposited by the beam inside the target. And usually, we are aiming for a target temperature at around 2000 degrees Celsius. And this high temperature will help the radioactive atoms to diffuse out of the target material. Okay, let's go inside of one target. If you look here, you have a figure that shows an artistical view of the trajectory that follows radioactive atoms that diffuse out of a target. This is a very stochastic process. So the radioactive atoms will randomly walk inside of the material, and at some point it will escape this target material, ending the diffusion process. This process is extremely chemistry dependent. The diffusion speed varies greatly from one element to another, and it is also very temperature dependent. To illustrate this, I've shown you the first equation, that is the diffusion coefficient. It tells you how fast an atom will diffuse outside of a target. And the diffusion speed increase exponentially with temperature. And this is why we want to achieve, usually we want to achieve a temperature of the target that is as high as possible. The second equation gives you the average diffusion time as a function of the target thickness, little d, and the diffusion speed. Please note that the diffusion time decreases quadratically with diffusion length. So having a very small diffusion length really help for having a fast diffusion time. And now there's this question. Fast diffusion, why does it matter? Why do we want to have a fast diffusion of radioactive atoms outside of target? Well, there's a competition between diffusion time and radioactive decay. If we look at the formula that I've shown you earlier, the second term, efficiency release, will depend of the time, the diffusion time and the half-life of isotopes. For instance, if the diffusion time is way bigger than the half-life of the nuclei that we want to produce, then the release efficiency is near zero. So if we want to have a high overall efficiency, what we need is diffusion time to be smaller than the half-life of the isotope of interest. And to allow this very fast diffusion time, a key aspect in the making of a good target is microstructure. On this figure, there is 4 pictures of different carbon material. They're all made of carbon, but their microstructure differs. Little a, for instance, is a flaky graphite. B is a POCO, a very dense and not porous carbon material. And D and C, they are carbon nanotubes with high porosity. And for the same element, a target has vastly different diffusion times depending on microstructure, porosity, and density. And there is a lot of research and development on that subject. Diffusion is also one of the steps where some of the elements won't be able to be produced. For instance, some elements diffuse very easily outside of target, like alkali elements and noble gases, and it's almost impossible for refractory element. So if you look at this periodic table that shows you all the elements that have been produced in ISOL day, you can see that some elements are not produced. And then why is it the case? Why cannot produce this specific element? And if we look at the second periodic table that gives you the temperature of the melting point, sorry, for each element, you can see that there is a clear trend. The element with the higher melting point are not able to be produced at ISOL day. Usually, a good rule of thumb is to consider that if the melting point is above 2000 degrees Celsius, it is almost impossible to extract this element out of a target. But please note that some ISOL facilities still make refractory element beam. For instance, ISOL in Jyväskylä, Finland, do that quite easily. Okay, so for the takeaway of diffusion, chemistry matters. The target materials varies depending on the isotope to be produced. Some elements are not available. For instance, a refractory element, well, they are refractory to change. I don't want to leave targets because they are very hard to do. And there is a competition between radioactive decay and diffusion time. And this is also one of the main reasons why very exotic nuclei cannot be produced using the ISOL method. Okay, and now for effusion, the next step. So after the radioactive atoms leave the target material, it will then have to travel from the target container up to the ion source. In a very similar fashion to diffusion, this process is random. So the radioactive atoms will fly from wall to wall inside the target container, travel through the transfer tube, and then end up in the ion source where it will be ionized. And effusion is similar to diffusion because it takes time, it is chemistry dependent, and it is also temperature dependent. And usually, the hotter, the better. In most cases, though, effusion takes less time than diffusion. And there is a nice little trick to do in effusion, is that you could cool the transfer tube. And what it means is that the condensable element will condense and be trapped inside the transfer tube, and only the gaseous element will be able to go to the ion source to be ionized. And that can help to achieve some beam purity for some element. And the next step is ionization. There is three main flavors of ion source. The first one is surface ionization. Then you have electron impact ionization, and lastly, resonant laser ionization. The surface ionization ion source is the simpler. You just need to heat a tube. So if you have your transfer tube, it can also work as an ion source. And if it's heated at the right temperature and made of the right material, some of the atoms will leave an electron. It only works for atoms with small first ionization energy, so you'll be able only to produce alkali element and some other. So the advantages of this method is that it's very chemically selective, but the disadvantages is it's very chemically selective. So you can produce all of the elements. You can't produce all of the elements, sadly. The second method, it's using electron impact ionization. In this kind of ion source, the effusing atom that arrive inside the ion source encounter a plasma. Collision with electron will strip one electron away from the atom, creating a +1 atoms. This electron can be provided by several methods. The first one is to use a microwave heating of a plasma. The second would be to provide electron via emission from a hot cathode. And you could also use electric discharge inside of a gas. The advantages of this method is also its disadvantages. It is universal. It's able to produce almost all elements, but you won't have any chemical selectivity. The last method is resonant laser ionization. In this method, you would send at least two lasers inside of the transfer tube of your production system. And the principle is as follows. The first laser will bring one electron to an excited state, and then a second laser will bring this electron to an auto-ionization state, and that will ionize this element. And the great thing with this method is that the wavelength used to bring an electron to an excited state is very element dependent. So you will be able to ionize only one kind of atoms, one element. So the advantage is it's very chemically selective and it can perform science with just ionization. The disadvantages is that you need a different ionization scheme for each element. And not all elements are accessible. There is some technical limitation. We don't have access to all the wavelength that we want. And it also requires a laser room with laser people. So it needs a lot of resources to be able to use resonant laser ionization. Okay, and for the takeaway of ionization, so chemistry still managed to sneak in, and the available elements depend on the ionization method. For instance, with lasers, you have access to half of the periodic table with high chemical selectivity. With surface ionization, you have mostly alkali element, and again with high chemical selectivity. And with electron impact, you ionize everything, but you ionize everything. Laser ionization is most of the time harder to implement, but is often better, if possible. Okay, and the last step, now that we managed to produce a radioactive ion beam, what we want is to purify it. And for that, most of the time, the beam is separated using a magnetic dipole. A magnetic dipole will select only one kind of M over Q ratio. And as usually a radioactive ion source produce +1 ion, the dipole will select one mass only. And what does it mean? It means that isobaric contamination can be an issue depending on the kind of ion source you're using. And so a word on beam purity. So I'm not an expert in experiment, but I know that some of you really want to have pure beam and some other that don't really care. So beam purity matters depending on experiment. The beam composition is a result of every step in the ISOL method. So by choosing carefully what kind of your technical choices in each of these methods, you can have a beam that is very pure or is not very pure. The first step is to the production reaction. So cross-section varies greatly depending on the kind of target and beam and reaction you're choosing. Diffusion, effusion will also a second step for the beam purity. So chemistry and half-life will impact what kind of atoms and isotopes will be able to effuse up to the ion source. Then ionization will give you further chemical selectivity or not. And then lastly, the separation. Some separators have better separation power than others. Okay, so we are approaching the end of my talk. And this is a tutorial. So how to check if a beam is doable. The first step is to use your newly found knowledge and to go into your favorite nuclear chat and check the half-life. If the nucleus you want to produce has a half-life of a few nanoseconds, you can forget about it. It's not reachable, doable with the ISOL method. The second thing to check is its chemical property. Is it a very refractory element? Because if it is, it might be very complicated to produce it. And then you could also think about the nuclear, the production cross-section. If you want 10 to the 9 particles per second of an isotope that is near the drip line, usually it won't be doable. And the second step is to check if the beam has been produced or could be produced at the facility of your choice. And for that, you go on the internet, use your favorite search engine, and type yield or beam plus the ISOL facility name of your choice. And you could also look up on the website of each facility. And doing a quick search, I found a few links to have access to the beam that have been produced or could be produced. And the last step of this tutorial, once you've checked everything that you could do on your own, you could contact the expert in charge of the facility to have more information. Because sometimes online, you won't get access to information like beam purity or the ease of production, or if the beam is still doable to this day. And the bonus step would be to ask for the development of a new beam that have never been done before, because this is this kind of demands from the user that drive research and development in ISOL facility. And this tutorial concludes my talk, and I would like to thank you for attending my first lecture. And if there is any question,